This is homework help for the energy conservation practice, aka Little Piggy worksheet. For this worksheet, you're going to want to have your formula sheet or your notes handy because you'll need to use every equation we've talked about, including work, GPE, KE, EPE, work energy theorem, and then this long conservation of energy equation that was in the notes. You could, in fact, even add to that the elastic potential energy possibility. You will not have to use the full equation in every problem. So what you want to do in all of these is to think about each scenario separately in terms of what kind of energy does the object have at the beginning, what kind of energy does the object have at the end of the problem, and that's going to help you figure out what equations to use. So for example, if we look at number 1, Galileo is dropping objects off the Leaning Tower of Pisa to determine whether heavy or light objects fall faster. Okay, so here's our tower. Galileo is dropping off objects and they're going to fall and hit the ground. So at the beginning, the objects have GPE, right? Galileo is holding them at rest before he drops them, so they do not have KE. There's no reason to believe anything elastic is going on. And so that means the only kind of energy initial is GPE. And then as they fall, they lose GPE, right, as they lose height, and they gain KE as they increase in speed. So as the object hits the ground, all of the energy is now final kinetic energy. Okay, so knowing that, then we can look at A. It says, what would have been the change in GPE of the cannonball? Well, if you think in terms of givens, they gave you a mass in the problem. They gave you a height initial of 12 meters. We know the Leaning Tower of Pisa is on the Earth. So instead of using the long equation, if you're looking for change in GPE, just solve for GPE, right? M times G times H. You have the givens for that, and that will give you the answer. Okay, and then part B, what would be the ball's KE just before hitting the ground? Well, we just talked about how the final KE is equal to the initial GPE. So whatever the answer you had up here will equal the answer for KE final. Okay? I hope that makes sense. Okay, if we look at number 2, Brittany is changing her tire on a hill, a couple of hills, right? So get yourself a visual if you need it, and then we're going to look at the givens throughout the problem. So the first hill is 20 meters high. That's going to be our initial height. She trips and drops the tire, so it actually has an initial speed of 2 meters per second at the top of that hill. It rolls and lands up on the next hill, which has a height of 5 meters, so that's going to be our final height. And then the question is, how fast is it moving? So we're looking for final velocity. Okay, so in this problem, if we think about types of energy, the tire has GPE at the top, right at the beginning, and it also has KE at the beginning because it's moving. And then at the end of the problem, it's got GPE because we're not flat on the ground anymore, and it also has KE because we're trying to find a final velocity, so this tire has not stopped yet. So for this equation, you're going to actually want to use the whole long conservation equation that says GPEI plus KEI equals GPEF plus KEF. I think that I reversed my GPEs and my KEs from the way it's written on the formula sheet. Just FYI, it doesn't matter if you do GPE or KE first. So if we write those equations out, that gives us mg times hi plus 1/2 mvi squared on the left side equals mghf plus 1/2 mvf squared. You can actually cross out the masses because we're talking about the same tire throughout the equation, and so that mass would cancel itself out anyway. And then from there, you're just going to plug in numbers. So G is 9.8. I'm going to skip writing the units for the sake of space here. If you do that, just make sure you're writing the correct numbers in the correct spots. Okay, so I have 9.8 times 20 plus 1/2 times 2 meters per second, and I need to square that, equal to 9.8 times 5 meters plus 1/2 times an unknown final velocity squared. To solve that, I'm going to just work little by little. So 9.8 times 20 is 196. 2 squared times 1/2 is 2. 9.8 times 5 is 49. And then I still have 1/2 times VF squared here. So now I'm going to add 198 equals 49 plus 1/2 VF squared. Sorry guys, I'm running out of room. I'm just going to write over the type. So I'm going to subtract 49 next to get it off of the right, which gives me 149 equals 1/2 VF squared. I divide by 1/2. That is 298 equals VF squared, but I just want VF. I don't want VF squared. So my last step is to take the square root, and that gives me a final velocity of 17.3 meters per second. So this tire is cooking. It's gone from 2 to 17. It's gained a whole lot of kinetic energy in the loss of gravitational potential energy. Okay, so that's number 2. Number 3, I want to give you a little bit of a hint so we can see it. I'm going to erase what I did for number 2 here. So number 3 says, now we have friction on the hills. So her tire shouldn't actually be going as fast as we just said it was. As a reminder, we said it was moving at 17.3 on number 2 is the theoretical speed. That's how fast it should have been going. It was not going that fast. And so it actually only reached 3 meters instead of 5 meters at the end. It didn't make it as high up the hill. Okay, so how much energy was lost to friction? So what you're going to want to do here is figure out how much energy final should it have had. So we're going to do mass times acceleration due to gravity times final height theoretical. Okay, so that's going to use this 5 meter final height. And then you're going to find the actual GPE final by doing the mass times the gravity times the actual final height of 3 meters. Okay, and then the energy lost, or the change in energy, will equal the difference between them. So it's going to be that GPE final that the tire should have had, the theoretical, minus the GPE actual that the tire had. Okay, so anytime you've got a problem asking for energy lost, you need to figure out what should have been the energy and then what was it actually, and subtract the difference. Okay, last problem that I want to look at is this pig one on the back. I'm not going to work out the whole thing. I just want to walk you through using the big equation, but not using the whole thing. Okay, so we've got a pig on the top of the hill. The problem tells you that the hill is 100 meters long, but it also tells you that it has a vertical drop of 30 meters. Okay, so if we're thinking about information that we actually need, we need heights, right? So HI is going to be the 30 meters. And then we're going to assume that HF at the bottom of the hill is 0. Okay. The pig is standing at the top of the hill. So initially he has 0 speed. But then we can assume if he's flying down this hill, he's going to have some final speed. And that's actually what the question is asking us to find. Okay, so let's think about types of energy. At the top of the hill, he has GPE, right? Because of this initial height, but he does not have KE because that KE initial would be 0 since he didn't have any speed, right? So we can eliminate that. At the bottom of the hill, we can assume that he has a final KE because he's moving. However, he does not have any GPE because his height is 0. So we're going to X that out. Okay, so in the long equation that says GPE I plus KEI equals GPEF plus KEF, we want to only keep the ones that he actually has. So he has GPEI and he has KEF. And we want to get rid of everything else that wasn't present. So we're going to get rid of KEI, we're going to get rid of GPEF. Okay, so our equation is going to say MGHI equals 1/2 MVF squared. Like in the other problems, you can put in the mass if you want, or you can cross it out because it's the same pig on both sides of the formula. So if you do that, you've got a significantly simplified equation. You have GHI equals 1/2 VF squared, and now that is not so bad at all to find. Hope that helps. As always, reach out if you need to or you have questions.